Welcome to the Bioprinting Masterclass, where we'll explore how 3D tissue engineering and regenerative medicine intersect with additive manufacturing. Over this 30-slide deck, we'll cover bioinks and materials, printing technologies, applications in tissue engineering, and the clinical and ethical steps needed to translate lab advances to patient care. This slide lays out our compact covenant for the session. Crisp pacing, zero fluff, practical takeaways, and one shareable insight per participant. In short, expect focused, actionable content designed to keep attention high and enable immediate application, so you can absorb core ideas without getting lost in detail. Bioprinting automates tissue creation by depositing living cells, biomaterials, and bioactive agents layer by layer to build functional 3D tissues and organs. The central idea is merging additive manufacturing precision with biological design, so constructs can perform physiological roles and ultimately support regenerative medicine applications. Here we frame the problem and promise: donor shortages, repeat surgeries, and ethical limits on animal testing drive demand, while bioprinting offers on-demand living constructs, patient-matched grafts, faster drug screening, and ethical alternatives that could accelerate regenerative solutions and reduce reliance on scarce donor tissue. This page focuses on bioinks, the engineered materials that carry cells and signals during printing. Effective bioinks encapsulate cells, cross-link rapidly, degrade in sync with tissue formation, and present biochemical cues to guide proliferation, differentiation, and matrix deposition, so the printed construct can mature into functional tissue. Choosing the right cell source requires balancing immune compatibility, scalability, and function. Autologous cells reduce rejection, iPSCs offer patient-matched, scalable supplies, and primary cells provide immediate functionality, so selection depends on expansion time, regulatory hurdles, potency needs, and the intended clinical application. In Module 1, we examine temporary 3D frameworks and material tuning. Scaffolds define geometry, mechanical properties, and vascular channels, while materials range from decellularized ECM to synthetic polymers tuned for stiffness, degradation rate, and bioactivity to orchestrate remodeling and support tissue regeneration. Rapid solidification is a key enabler in bioprinting, and we compare three mechanisms. Photopolymerization gives fast, high-fidelity curing, but can risk cell damage. Ionic gelation is gentle and quick, with limited mechanics, and enzymatic reactions offer biocompatibility with slower kinetics, so trade-offs must be optimized for functional tissue. Extrusion bioprinting uses pneumatic or screw-driven syringes to deposit viscous bioinks, supporting high cell densities and low cost. But it sacrifices fine resolution. Choosing between air pressure control and screw rotation depends on throughput, viscosity, compatibility, and the balance between feature fidelity and cell viability. Droplet-based bioprinting generates tiny picoliter droplets using thermal or piezoelectric actuation, enabling rapid, high-precision patterning with minimal shear stress, but it requires low viscosity bioinks and typically limits cell concentration, so it's ideal for multi-per-cell patterning rather than dense, organy-scale constructs. Laser-assisted bioprinting offers contactless, micrometer precision by transferring cell microdroplets from a donor slide to a target surface using focused laser pulses. The advantage is high resolution and minimal mechanical stress, while challenges include specialized absorbing layers, lower throughput, and higher equipment costs. Digital light processing, or DLP bioprinting, cures whole layers simultaneously to achieve sub-150 micron resolution and smooth surfaces, enabling continuous printing, but light penetration, depth, and photoinitiator, cytotoxicity, limit, construct thickness, and demand careful material selection for biocompatibility. Transforming medical imaging into bioprintable GE code starts with CT or MRI segmentation to capture organ geometry and vessel trees, Then computational conversion assigns materials to voxels and outputs GGAC code, so printers can fabricate patient-specific constructs that aim to restore physiological function and fit. GMPO-compliant bioreactor expansion turns isolated progenitors into billion-cell doses by using stirred tank systems with automated feeding, oxygen control, and real-time monitoring, enabling consistent quality, genomic stability, and lineage potency within weeks to support downstream bioprinting or cell therapies. Achieving deposition accuracy relies on coordinated material deposition, engineered vascular lumina using fugitive inks, and real-time optical feedback to correct drift. Together, these approaches enable sub-100 micron feature accuracy across centimeter-scale constructs, which is critical for reliable, functional tissue fabrication. This slide summarizes solidification methods across platforms: photopolymerization, ionic gelation, and thermal gelation. Each locks spatial organization within seconds while maintaining high cell viability, and the common outcome is rapid stabilization, precise control over structure, and support for subsequent tissue maturation. Vascularization is the central barrier beyond about 200 micrometers, since thicker cell blocks risk hypoxia and necrosis. Strategies like co-printing endothelial channels, integrating microfluidic perfusion, and in vivo prevascularization aim to extend viable tissue thickness toward organ dimensions by restoring oxygen and nutrient flow. Hierarchical vascular tree bioprinting combines extrusion and electrospinning to recreate macroarteries down to microcapillaries, often using sacrificial inks that dissolve to form interconnected lumens, and this physiological network architecture supports perfusion at realistic flow rates needed for tissue survival and maturation. Surgical integration of printed grafts requires reliable vessel connections, leakage reduction through biocompatible glues or stents, and endothelial lining development to prevent thrombosis. Successful integration means the graft's intima fully incorporates with host vessels and restores functional blood flow. Closed eddy-loop perfusion systems accelerate tissue maturation by supplying oxygen and nutrients, removing metabolic waste, and applying mechanical cues like pulsatile flow. Optimized pre-implantation conditions improve ECM deposition, barrier function, and readiness for implantation, shortening the path to viable grafts. A marketer-ready bedside bioprinting application is burn wound closure, using autologous keratinocytes and fibroblasts printed into a collagen hydrogel directly at the bedside, which can close wounds faster, reduce infection, and minimize scarring, representing a tangible clinical translation milestone. Gradient scaffolds enable cartilage and bone regeneration by printing zonal bioinks that mimic cartilage surface and subchondral bone, promoting integration and tissue formation so patients can regain painless mobility and potentially delay or avoid total joint replacement in active adults. Vascularized bone flaps for mandibular reconstruction use a printed ceramic polymer matrix seeded with stem and endothelial progenitor cells to grow bone with an internal vascular network, enabling functional load-bearing and integration with native vasculature to repair complex mandibular defects. Bioprinted hepatic models recreate multicellular liver architecture using iPSC-derived hepatocytes, stellate, and Kupffer cells to provide superior drug toxicity prediction compared with 2YD cultures, accelerating pharmaceutical development while reducing animal testing through more accurate human-irrelevant assays. Scaling to clinically relevant throughput is a major challenge because high-resolution single-cell patterning remains slow. Emerging solutions include parallelization, continuous projection printing, and faster optimized bioinks to increase deposition rates and bring organy-scale fabrication within reach. Immune stealth and graft survival strategies weigh off-the-shelf allogeneic bioinks against engineered universal donor iPSC lines. The goal is to balance accessibility and efficacy by combining immunitated cells with localized immunomodulation to improve graft survival and lower manufacturing costs. lack of standardized bioink formulations, inconsistent cross-linking protocols, and unclear quality metrics hamper reproducibility. Moving toward community-driven part registries, ASTM guidelines, and harmonized regulatory submissions will help align workflows and enable scalable tissue engineering. Current bioprinting costs are driven by expensive reagents, manual handling, and long bioreactor maturation. But automation, closed-loop sensors, single-use perfusion, and projected tenfold cost cuts can move the field toward reimbursable procedures and wider clinical adoption. To conclude, here are 10 actionable pillars, from bioink design and printing modalities to vascular strategy, clinical proofs, cost roadmaps, and ethical standards that form a practical roadmap for translating bioprinting innovations into real-world patient solutions and further exploration. Keep the conversation going. Share your top insight with the hashtag #DrMicroLearning. Connect with peers and join the community dialogue so we can continue refining ideas, celebrate standout contributions, and keep the curiosity pulse alive well beyond this session.